This is Webassign Week 9, Problem 3. First off, make a note that I have changed the problem description a little bit, so there's more text there. If you did this problem earlier and haven't downloaded the new version, you might want to just take a look at that. Make sure that you see the new description has a little bit more to explain what the situation is. That's perhaps the first difficulty. What in the world are we looking at? So if you read the new description, it's a simple coil with some turns of wire. It's got a rotation axis in the plane of the loops of wire, and then it's placed in a uniform magnetic field perpendicular to the rotation axis and rotated. So here I have a much larger coil, but it's the same kind of thing. So here's a coil with a rotation axis in the plane of the loops, the axis pointing right through here. And I can rotate this thing around, and you can imagine putting this into a magnetic field and rotating it at some steady speed. And then with some sort of connection to the coils, that would have to take some extra mechanism that could connect to the coils while they're still rotating, slip rings of some sort. And then we're able to read a value that is supposed to be some number that you have in your problem. In my case, it's 360 microvolts. So let's draw the situation now. Here's our coil, and this would be the rotation axis. And we can have it rotating around kind of like this. And then we've got a B field perpendicular to that axis of rotation, something like this. And that's what we're trying to find. We don't know what the B field is. Okay, and in my case, the coil has 4 turns. So the wire is wrapped around there 4 times. The diameter is 1 centimeter, and from that we can figure out the area of the loop. And so we can get the flux through the loop, the flux being the B field times the area. But that flux is changing as this thing rotates. So we have to think a little bit more in detail about that. Note, by the way, you're given the diameter, not the radius. That might be another thing that would trip you up. So let's draw a picture of this sort of from an end view here. And now imagine that our coil looks something like this. So those are our 4 turns, and the coil is rotating about an axis like this. But now let's change the point of view and say, well, let's jump into the frame of reference of the coil. And in that frame of reference, it's the field that's rotating. And so if the coil is turning this way, the field would be going the other way. If we jump onto the coil, it looks like now the field is rotating. And so now you have a B field that is doing this sort of thing. And what we could do is imagine what is the angle of that B field, that little angle right there. Draw that a little bit larger, and we can see what we're talking about. So that's the angle of the B field. As this thing rotates, that angle changes and it increases steadily. So we're going to need to, we're told what the EMF is, and we have to get the B field. The relationship between EMF and B field, of course, is that the EMF is minus d phi dt, where phi is the, well, we'll call it the perpendicular component of the B field times the area. So we're going to have to somehow write an expression for B field times area, take the derivative of that, relate it to this EMF. So let's get the area first of all. That's a quick and easy thing to do. The area is going to be pi times the radius squared. It's a circle, presumably. So that's pi times half the diameter squared. So that's pi times 0.01 meters divided by 2, quantity squared, and I get 7.85 times 10 to the minus 5 square meters. That's the area. And I think that's the same for everybody. That number doesn't particularly change. But how do we get this flux? How do we express that when this angle is changing? If you think about it, it's going to depend. We want to know what the perpendicular component of the B field is. So we'd be finding this B perpendicular when B is over here, and this is B perpendicular. And that's just a cosine effect. So this would be B times the cosine of theta times the area. Now we're still trying to figure out that B. We're going to have to carry this through the very end of the problem. We'll solve for B. But for now, we just keep going. What about theta? How does theta change? Well, theta is just going to increase steadily with time. And that is where you put in one of these expressions where theta is just omega times t. It's the angular velocity times time gives you the angle theta. And omega is given to us in the problem, at least my numbers were that it was 10 revolutions per second. But to make all of this work, we have to put it in radians. And so that's 10 revolutions per second, and then times 2 pi radians per revolution. So omega is now going to be 62.8. That would be radians per second. That would be the angular speed omega. So now we could write our flux. Let's start with the flux. The flux is going to be B times the cosine of 62.8 radians per second t, and then times this area of 7.85 times 10 to the minus 5 square meters. And now we have to take the derivative of that. So the EMF is minus d phi dt, so we've got to take the derivative of that whole expression. Oh, and I forgot one thing. I forgot the number of turns up here. N is 4. I should have put that all the way up here. N times B times A. So that's N times B cosine theta times A. So there's an N that comes in right here. Or I guess I should put right in here. I might as well put the number. It would just be 4 in my case times B. Okay, so taking that derivative, we're taking the derivative with respect to time. And the rest of these things are constants. So we will have 4 times the 7.85 still comes out 7.85 times 10 to the minus 5. I'll skip the units for now. And then this 62.8t, this is cosine of 62.8t. So cosine of something times t, when you take the derivative of that, you get the sine of that same something, 62.8 times t. And then the something also comes out in front, 62.8. So that's an expression for the EMF, a general expression for the EMF. What we're told in the problem, though, is that the maximum value of the EMF. So the EMF is doing some kind of, if we make a drawing of it, the EMF versus time would be doing something like this. And now, well, actually, that's probably the flux would look like that. and then the EMF would be a sine function, like so. But the maximum value of the EMF is what we're given, and that's just the amplitude. So right here, oh, I lost something. I lost a B in here, didn't I? I neglected to include B, so let's put it in there. 4 times B. It's also a constant, so it still just floats along like everything else. So now all of this stuff out in front of the sine function is the maximum value of the EMF. So what we can say is the maximum value of the EMF I'm given in the problem was 360 microvolts. So that's 10 to the minus 6 volts. And that equals 4B 7.85 times 10 to the minus 5 times 62.8. And now I just solve for B. And so we find that B is going to be 360 times 10 to the minus 6 divided by 4 times 7.85 times 10 to the minus 5 and 62.8. And I don't think there's a lot of point in putting the units in here. All we would do is disappoint Joel one more time. You'd have volts up here, and N doesn't have units. 7.85, I think, is square meters. Volts per square meter per, well, volts seconds per square meter is what you'd end up with. This, if you multiply it out, comes out to the correct answer, which I don't have written down here. But anyhow, I did check it earlier, and it works. So there you go. That is problem number 3.